Okay, so we can get started here. So welcome back to Wednesday lecture. We are there. We are. Um, yeah. So um, we are nearing the end of our time together. So we have one big concept to still cover, and that is of regression. Now, we it has a kind of a sub concept of correlation that we'll spend most of our time today talking about. So we won't actually get to running regressions quite yet, but that's kind of what chapter 13 and 14 are revolving around. And this is perhaps I would say the most commonly used um, statistical technique, at least as far as kind of end game technique. So obviously we use, as we'll see, we'll use standard deviation here. And so standard deviation and some of those things I've mentioned along the way are heavily used. But what a lot of people do is take some data and run some regressions. Okay, so this is heavily used across academia, business, just people pull up data for fun, if you can believe it, and run regressions on baseball statistics and football data and whatnot. So this is heavily used, and so it'll be hopefully eye-opening to see this a little bit in action. Now it is a broad concept, and we are not going to become masters of regression, but our goal here is to kind of introduce it, see it in action a little bit, and set you up for either further study, whether you take another statistics class, something like econometrics, which we have here at Hamline. So if you've been enjoying this material, enjoying might be a strong term, but if you find some interest in it, look into that class, for instance. So whether or not you dig deeper into it with formal classes, or if you want to start reading up on further techniques, this is a good technique to kind of get your feet wet with. So 13 and 14 are highly connected in the broad sense. Before we get into kind of maybe what I'm specifically talking about, chapter 13 is we're going to be comparing two variables. So we're going to talk about how can we describe the relationship between two variables, and then in 14 we're going to say, now what if I want to throw a bunch of variables into this mix, and so we'll use the same techniques of these two variables. So you can think broadly kind of a scatter plot. We're going to be dealing with scatter plots a lot today. So two variables, how are they related? 14, we say, what if I have 37 variables? Or what if I have 3 variables? And we'll see how we can broaden our techniques to incorporate those. And so maybe you can see why this, specifically the stuff in chapter 14 is heavily used, is because we can take a bunch of variables and distill it down into some useful concepts. So today we're going to cover the foundational piece of regression, which is correlation. And so I think that'll take up our time today. And so then on Friday we'll turn and we'll look at regression. We'll turn to Excel on Friday and look at a few things in correlation, and then we'll turn to regression, and then that'll carry us into next week. We have we'll be together through next Wednesday, at least. And then I think we're calling it reading week or something like that. There you have a week of kind of study before finals starts. So there'll be no new material there. I will continue to have office hours and maybe add an extra office hour in there during that reading week, just so you are aware that as you're studying, we can meet during that week. A couple other things before we jump into correlation. So this chapter 13 and 14, I've smushed it together into one Connect assignment. So you have one last assignment to do for that, and that is it's posted and it's due next Wednesday, so a week from today. So I know that doesn't fit what I think I promised you Tuesday, Friday, or Saturday. So you can treat this as do it Tuesday. I've just given you to that last day, Wednesday, to do it. So, yeah. So, and then other things to note, there is that problem set 3 is up and going, and that has, just to remind you, I emailed this out, but it has you play around in Excel and do some of those 2 sample tests that we've been working in chapter 10 and 11. And a little bit, 2 samples in 11, so it has you do a few 2 sample tests, and then I have you kind of recreate kind of a 1 sample testing process, like we saw in chapter 10. So if you were with us on Friday, the problem set will look very familiar. It's much of what I ran through in that lecture, that technologically difficult lecture. So I re-recorded some of it. So that is posted online on Canvas. So if you weren't there and you haven't watched that, please take a look at that. I'm sure it will help you a lot in what I'm wanting on the problem set. So please take a look at that. And I think I have that set up to be due this Sunday. So it hopefully won't take you too long if you've watched Friday's lecture. Okay, so I think that's enough kind of general housekeeping. So today we're going to talk about correlation and jump into that. Now correlation is something that we've touched on a little bit already, and in fact, it's heavily related to what we covered in. It was either chapter 3 or 4 when we talked about scatter plots. We looked at scatter plots as a way to describe or visually depict 2 variables. Right along the time we were talking about pivot tables and whatnot. We looked at scatter plots. How do we describe the relationship between 2 variables? And we went so far as to say, these 2 variables seem to have a positive relationship, or even a strong positive relationship, or a weak negative relationship. We use these types of terminology, and in fact, we use that here with correlation. And so what we're going to do with correlation is put a numerical value to that. But even with correlation, we sometimes use that same terminology, strong positive relationship. So I'm going to pull up. And we're just going to, for the first little bit of time here, we're just going to play around with some of those scatter plots and how we might describe the relationship. If we had data and that looked, let me just plot some data out. Just kind of randomly out here. What we talked about in the scatter plot is that sometimes we can describe that these 2 variables tend to either move together or move opposite. So for instance, we might say that the red data points up above, they tend to move together. They move in the same direction. That being that when X increases, it goes further to the right, and when Y increases, it goes higher, right? So if we have more of X, you tend to have more Y. Okay, not always, but typically they move together. They move in the same direction. And so back when we dealt with scatter plots, we said that was a positive relationship. And whereas we may have data that moves in the opposite direction of each other, right? So in this case, as X, drawn X correctly, as X increases and moves to the right, Y tends to decrease. And so we'd say that this is a negative relationship. And we also said we would use terms like, up above, maybe it's a moderately positive relationship. Whereas down below in the yellow, that was a strong negative relationship, right? So it was a tighter connection between the 2, that almost every time that X increased, Y also decreased. There's a stronger connection. And one way to think about that is if we were to draw kind of a line that best fit the data. And we'll be more specific about what we mean by best fit when we turn and talk about regression. But you can think about it as, can I get a line that's pretty close to these data points? And we can see that it's much easier to fit a nice line, and I might be off a little bit, but the data points in the yellow are tighter around that line, right? They don't jump around relative to the line. And so that's a stronger relationship. The connection there is stronger between the X and Y. It's also negative. Okay, so yeah, so much of what we're doing with correlation is what we covered in scatter plots. And in fact, other textbooks, you'll see correlation actually slid up and talked about early on in this descriptive statistics, because at the base of it, correlation is a descriptive statistic. We use it in the term, just like when we talk about, the mean and the median and the for one variable. When we talk about describing two variables, we'll use things like pivot tables, scatter plots, and correlation. So correlation is a descriptive statistic of the connection or the relationship between two variables. So we've got it here. We set it aside for a while because it fits very nicely with this powerful tool of regression, in that it forms the backbone of regression. So it makes sense in both places. We've just chose to kind of set it aside until now. Yeah. I was going to try to... I don't know if this will be confusing, but I'm going to say it. So correlation between two variables is on the kind of the same level as importance as standard deviation is to one variable, right? So standard deviation talks about how much one variable moves around, and correlation talks about how much do two variables move together or opposite. Okay, so it has a very similar place of importance in terms of describing the relationship of two variables as standard deviation does with movement of one variable. That's the first time I've made that analogy, so I'm trying to make sure that makes sense, but I'll stand by it for now. So you can think of it in similar terms or similar importance. Okay, so I've said we're going to put a numerical value to this, and that value is going to be between -1 and 1. So it's always going to be between -1 and 1. I'm putting these in square brackets, so mathematically that means that contains that value. So it can be -1 and it can be 1. We also the letter we use is R, so that stands for correlation. Maybe because there's two R's in it, I don't know. So R is the correlation, and it spans from -1 to 1. It's always within that, okay? And that includes 0, right? So 0 is in there, and 0 means something in correlation as well. Okay, so correlation gives us two bits of information. It tells us the sign. We have either negative or positive, which is a negative or a positive relationship, right? So this is a negative. This would be a negative value down here, and this would be a positive value up top. So we get that piece of information. We also have the strength of it, okay? And the strength is how far towards either -1 or 1 that you are, okay? So that can be, it's not a one-directional measure of strength. So we can think about it maybe on a number line. We have -1 over here, and we have 1 over on the other side, and both of those are strong correlations. Okay, so this is strong negative, and this is strong positive. Okay, I realize I'm in the way. Okay, so we're learning when we see a correlation, we know the sign, whether they move together or move opposite, right? So the red dots up here move together as X is larger, Y is larger, so that's a positive correlation. But it's not as strong as the yellow, right? So I'm just going to pick, just based on experience, this might be R of 0.92 or something. No, that is wrong. R of -0.92. Okay, so a fairly strong relationship. And one way to visualize that is that if we had that line in there, they'd be pretty tight to that line. Okay, up top, this isn't a weak correlation, but it might be something like R of 0.62. Okay, it might be a little less than that, but something in that range. And so going back to our number line, again, we'll eventually learn how we exactly calculate this, but I kind of want to set us up for what to anticipate. So we have 0 in the middle, and 0 is saying that there's no relationship, right? And we can have that. Okay, just to add more complexity to the screen, we can have no correlation. In fact, a lot of variables are uncorrelated with one another, right? There's all kinds of scenarios where we would assume that there's no connection between, the number of books you own and your hair color, your height. I don't know. Two variables that are not connected in any way. We could see the data points just kind of be a big mismatch of nothing and have no connection to one another. Okay, and so we wouldn't see much of a correlation. It could be R is equal to 0. It might be something like R is equal to 0.02 or 0.10 or something, a small r. And so we typically talk about values that are close to 0 as being weak. Okay, so there'd be a weak negative and a weak positive, right? But values that are close to 0, we have this kind of middle ground that we often say is moderately positive, okay? And there'd be a moderately negative. Now, I say all this, there's no defining line. So there's no, some texts might give you kind of a rule of thumb. You might find, okay, values between this and that might be moderate, but there's no definitive value that you say, okay, 0.61 is moderate and 0.62 is strong. There's no line like that. In fact, we only use these terms to kind of speed up the process of talking about correlations, because at the heart of it, we have a correlation for all of these. So we could just report the actual correlation. So the only time we use terms like strongly positive, because in some sense, we don't care if this said 0.92 or 0.93. This is not the yellow. So we use terms like strongly negative to refer to the yellow case here, because we don't, maybe in that case, we're not that concerned if it's negative 0.92 or negative 0.93. Okay, so these terms just kind of help us talk about what the correlation is without spitting out a bunch of numbers. But we do often calculate the exact value because, number one, sometimes it's helpful to be able to repeat the exact number. But then also, as I said, this is the building block of regression, and there we use the correlation value in those calculations. Okay, so at the heart of it, we're describing how well these two variables move together. I do wanna just cover a couple things before we crunch the numbers. I wanna kind of mention a few hiccups that people often have when they jump into correlation. So number one, we are talking about a linear relationship. Okay, so it's what correlation is doing is summarizing the linear relationship of two quantitative variables, and it's putting it into one number. Okay, so this can break down when we have nonlinear relationships, and we'll take a look at that probably next week. Just some cases where we do want to be mindful that this is forcing it into a linear relationship. So if you have some kind of curvature to your data, this is not going to pick that up. And we are taking an average. And so we're taking an average. So that means that there are going to be cases or scenarios where certain observations are not going to follow the general trend. All right. So this is an average trend, an average connection. And so that means when we plot data, we might show a positive relationship. Okay, let me just draw some kind of smattering of data. And maybe this is something like height versus weight. Just pick and put weight there, and we'll put height up here on the y-axis. And so what we probably would expect, and I'm sure the data, real data beyond what I just smattered out here, probably shows this to be true, that there's a strong connection, or relatively strong, or maybe this looks more moderate, but there's some relationship between height and weight, right? So as people, when people weigh more, they tend to be taller, and vice versa. Okay, and in fact, we could probably draw a line in there, and there'd be some positive relationship between the two. But of course, this does not mean that everybody follows that. It's not that if you have one person of a certain height and weight, any other person that's taller isn't necessarily going to be heavier, right? And we're going to have, thin, tall people. We're going to have people way up. Kevin Garnett is super tall, and he's probably still fairly heavy, but not Shaq level. And we're going to have some short, stocky people. So this correlation does not mean that it is always true for every observation. The other thing I want to mention is that correlation is not the slope. Okay, so a strong correlation is not a strong slope, right? So it doesn't mean that if you increase the height, the weight increases a lot. And to highlight that, I'm going to draw two sets of data, okay, that are fairly highly correlated. Okay, so this set here could have maybe this is R of 0.97. Okay, and if I would have drawn it a little closer, maybe I could have got it to 1, but it looks like I'm not exactly in line. But this is a strong correlation. Okay, but this, the one I'm going to draw here, is also a strong correlation. And both are going to be positive. Okay, so this, again, if I've done okay, let's say I did it well, and this could also be a strong correlation, a strong positive correlation of 0.97. But what we can see is that the slopes are different, right? It'd be easier if my axes were straight, but clearly the first one I drew has a much higher slope. Okay, so rise over run, recalling all the way back, it's got a higher slope than the second case, but they both can have the same strong correlation. Okay, so again, correlation is how well they move together. How well can we say, how Y is going to change if we know how X changed? So do they move in lockstep with one another? Not the level of their slope. So I want to point that out before we go into calculating, because we are going to be later talking about slope and interacting this correlation to find slopes. So regression is mainly, to jump ahead of ourselves, what is regression doing? Well, in the simplest case, it's finding this line. Okay, these lines that I've been drawing out here. Regression is going to find what those lines are, and the slope is going to be important in that. But it's not the correlation. Okay, the correlation is going to help us find that slope, but it's not the same thing. So just saying that about 12 times, so I only have to say it 3 more times when I get to it. Yeah, so the other thing that I'll mention now, again, we'll talk about it more in the future, but this one, so correlation does not equal slope. It's maybe a new thing for you, but this perhaps is not. Correlation does not equal causation. Okay? That term, hopefully you've at least heard it. And so that's just something to keep in mind, that we're not talking about a causal relationship yet. We'll talk about how we might try to tease that out, but we're not showing any causal relationship. Okay, so there's no a higher weight does not cause you to be taller, but there might be a connection, and maybe there is some rationale there. But yeah, so I just want to put that on the forefront as well. We'll talk about that more heavily. So let's get let's get one last step in before we actually crunch some numbers and calculate our correlation. And the last step I want to do is adding in one other data point. Okay, and I think we can actually do it on what we have up here. So height and weight. These are two variables. Both variables we could find an average for, right? There's in our data set that I've plotted randomly here, there would be an average weight. So if we think about, and let's see if I can kind of, maybe that's going to be here. I'm just going to call that X bar. Okay. There's also going to be a height average, and we'll put that here. Okay. I kind of regret doing this here because I don't want that. I kind of want to take this bar out of here. So bear with me as I try to recreate what I had there. I just don't want that black line in there. So, but there'd still be an X bar, Y bar. Okay, and what I'm going to do is I'm going to plot in the middle of this data set, or this scatter plot, X bar, Y bar. Okay, so that is the mean. One way to kind of refer to it, right? So this is X bar, Y bar. Actually get that out of the way too. It's going to get messy. So that's the middle of our data in kind of two-dimensional space. And we don't often actually put that in a scatter plot, but we always could. And it will be helpful or kind of instructive to think about this a few times. So one way to think about correlation, again, is do they tend to move together? We've said as weight gets higher, so as weight increases, does height typically increase? And we've said probably that's true. And one way to break that down is to think about it relative to the mean. So if one of our people is above the mean in weight as they move to the right, does that person tend to be above the mean in height? Okay, so for some of these people that is true. Okay, for instance, this person circled in blue they appear to be slightly above the mean in weight, and they're also kind of slightly above the mean in height. So that is indicative of the two variables moving together relative to the mean. Okay, and same is true for a few of these data points out here, right? So anything up to the top right of the mean, we have above the mean in height, above the mean in weight, and above the mean in height. Okay, so for a few of these, that's true. I can't quite tell. That might also be true. Some of those are pretty close to the mean. So we have some variables that are moving together. They're above the mean in both. Okay, it also is moving together if we are down here. Right, so in these cases, the person is below the mean in weight, but also below the mean in height. So in some sense, those observations have moved together relative to the mean. They've both dropped below the mean. Okay, and now let's contrast that with some of these other observations where, for instance, the three I've circled are above the mean in weight, but they're below the mean in height. Okay, so we have some short, stocky people where the two variables are moving opposite of each other. As one increased from the mean, the other one decreased from the mean. And of course, that is just flipped when we think about these other, the other kind of corner here. Okay, so these people are above the mean in height, but below the mean in weight. So some tall, skinny people. And in our case, we have kind of people in all four quadrants. And I say quadrants because let's go ahead and draw just a couple lines here and kind of split this into 4 quadrants. Okay. And so now what we have is kind of breaking these into these 4 quadrants, where 2 of them show observations that move together. So the top left, so the top left up there, I'm not in the right spot for this, but are moving together, and the bottom right are moving together. So the blue ones are showing positive relationship between the variables, and the red 2 quadrants are showing a negative relationship. And so what correlation is going to do is kind of smush all of this together and take in some sense an average result from these. Okay, so it's going to kind of weigh these against each other. Do we have more moving together and then opposite? Now it's not just counting, right? So if we counted, it looks like it's like 9 versus 6, but it's going to weight them based on how far away they are moving. Okay, so these ones that are in close, the ones that are in close are going to matter less than the ones that are further away. So correlation is trying to sum these up in some type of a weighted average. It's going to be a very similar calculation to when we did standard deviation. Okay, we're going to actually, in some sense, let me see how to say this. So when we did standard deviations, we squared the deviation from the mean, right? And what have we just been working with? We have a mean, the yellow dot that's behind the 2 bars. We have a mean, and we're going to calculate deviations from that mean, but we're going to do it in 2 directions. Okay, so just remember, let me get rid of this statement. So when we did standard deviation, when we were calculating S, we did x minus x bar. We squared it, okay, and then we took an average, right? And we summed all of that up, and we divided by n minus 1. We're going to do a very similar thing here to do correlation, but instead of squaring the deviation. So remember, just to reiterate, we have some deviations here. Each one of these we can measure how far did they deviate. So, this one deviated a certain distance. So this data point deviated a certain distance from the x mean, but it also deviated a certain distance from the y mean. So we have 2 deviations to mix up. Okay, so to kind of put into our calculation. So rather than squaring the deviation from the x, we're going to take the deviation from the x and multiply it by the deviation of the y. Okay, so our equation is going to look somewhat familiar. The top, however, is going to be x minus x bar, y minus y bar. Okay, so what does that become? Graphically, if what I'm about to draw in here is confusing, that's okay. But for some people, it helps to see this. We're actually calculating an area. Okay, the area of that rectangle deviation here instead of a square like we did. So if that doesn't help you, don't worry about it. You don't need to interpret it that way. But we're taking an area just like we did with standard deviation, right? We took a square area. In fact, I'm going to go one step further in our standard deviation calculation, and we haven't written it like this, but hopefully it's clear that this is the same if I don't run out of space, which I kind of did. Let me just write that a little cleaner. So we could rewrite this top as x minus x bar times x minus x bar, right? That's what the x minus x bar squared is. So I just hope that that's clear, that what we're doing is swapping one of those deviations out for a y deviation. So we're taking this out and we're putting in the y minus y bar. So the top is very close to what we've done in standard deviation. Okay, let's finish out this calculation. we're going to, again, do a type of mean. So just like we did with S, and we can do, so this is a sample correlation. Almost always we're dealing with samples, so we're just going to stick with the sample calculation. There is a version that divides by n, just like we did with sigma up above, right? There is a population version, so you divide by n, but we'll just stick with the n minus 1. But we're trying to take a sort of an average, and so far this matches. Now we're going to add in 2 other bits of information, and that is that we're actually going to use the standard deviations. So to finish out this equation, we add in Sx and Sy. Okay, so when we calculate correlation, we're forced to calculate standard deviation. So when you do this by hand, it gets quite gross. But why are we doing this? So what this does for us is that we are independent of the units. Okay, so what we're trying to do in the denominator is take into account how much do these variables move around, right? This should feel familiar. That's a lot of what our denominator has always been about, right? So even in our t-tests and whatnot, it's always been some deviation from the mean up top, right? And we have that here. And on the bottom, we're trying to take into account how much does stuff move around on its own. Okay, so same thing here. Deviations, let's multiply the deviations by themselves and then take into account movement of the variables. And so this does some things for us. For correlation, it's going to remove the units. So one way to highlight this, if we calculate the correlation of this height and weight, and we do it in, we measure height in inches, we'll get a certain correlation. Okay, so we'll have a correlation between height and weight. If we take our data and transform it into centimeters, okay, our same group of people move over to Europe. We run the same correlation, but we've measured in centimeters. We will get the same correlation. Okay, and that's extremely helpful. We don't have to report what units we're in. Okay, so you can simply say there's a 0.52 correlation between height and weight. We don't have to say 0.52 correlation between height and weight if you're measured in inches, and it's a 0.57 if you're measured in centimeters, right? That won't make sense because it will be the same. It'll be 0.52. If it's 0.52 in inches, it's 0.52 in centimeters. So that's incredibly helpful. And that's partly driven by the fact that we're taking into account how much these move around, right? So if we're in centimeters, they're going to move around more. So our deviations are going to be larger. But that's canceled out by the standard deviation. Okay, so that's really what the denominator is trying to do there. Put it into context as to how much they move around. All right, so let's so we have the formula. So I think now we're ready to actually crunch an example. Which will be easier if I have some numbers that are already in front of me. So let's jump over and we'll just rewrite this. So I'm going to rewrite the formula up here. And there we go. Yeah, so let's write this down. So R, very zoomed in. Okay, so R is the summation of the deviations from the X mean times the deviations from the Y mean. Okay, now notice we're not squaring those. So what's important about that is that we're not losing the negative, right? One of the reasons we squared in standard deviation, or one of the benefits, was that we took care of that negative problem, because when we added up, remember, it always summed to 0, and that was pointless for us. Here, we don't have that problem, and in fact, we need to make sure that we're carrying with the negative sign, because what's true about correlation? It ranges from -1 to 1, and that either the negative or the lack of the negative is important. So we're going to have to be mindful of not dropping that negative. We're dividing by n minus 1, and then we're incorporating that sx and sy. Okay, so fairly gross equation, but we know all of these parts and we know how to handle them. So we're going to look at an example, a very simple example, because I don't want to churn through a ton of observations and you don't want to watch me churn through a ton of observations. So let's walk through an example with just 4 data points. So let's say we have data from 4 households. And we have information on the number of kids they have. Okay, so household 1 has 4. This says 6, 8, and 10. Okay, so this might be some data from the mid-1960s or something when people had more kids. But we also have how much milk they drink per week in gallons. Okay, and of course I'm just making this data up, so you can guess that it's going to fit our preconceived notion that more kids means more milk drink. So we might be able to expect that there's a positive relationship, and because I'm making the data up, that's probably going to hold true, but maybe it wouldn't be in practice. So we're going to plot this. Again, we don't always have to plot the data, and but sometimes scatter plots are helpful, but also one of the benefits of correlation is that we don't have to plot all the data all the time. But let's plot it. Now, as I do this, I'm relying upon I've made some assumptions here, but those of you that are studying econ maybe this semester as well, you might be thinking, well, there might be some wealth effects, right? Maybe you're getting into elasticities and wealth effects, and you might think, well, more kids, wealth impact in a negative relationship. So I don't know what the actual data would show. So let's put kids down here. And so what do we have? We have 4. So let's go 2, 4, 6, 8, 10. Try to draw this somewhat to scale, but this is 4, 1. What do we have? We have 6 kids and 5 milk. We have 8 kids and 4 milk. And we have 10 kids and 6 milk. Okay, so I don't know how well I did there, but something like that. So that's our 4 data points, and now we're able to, or we can think about calculating this correlation. So I'm going to add in that, where do we start with correlation? What's the foundation of this equation? It's deviations from the mean, right? Just like standard deviation was, we're using deviations from the mean. So the first thing we have to do is calculate the deviation. No, the first thing we have to do is calculate the mean, right? We need the means to be able to calculate. So let's do that. So x bar, counting, just to clarify, we're counting this as x and this is y. What is this? This is 1828 divided by 4 is 7. So x bar is 7. There's an average of 7 kids per household. And y bar we have as 1016 divided by 4 is 4. So we have an x bar of 7 and a y bar of 4. I'm going to go ahead and plot that data point again. So 7 kids and 4 milk in there. Again, we don't always do that, but it can be helpful the first few times that we're sifting through this. So now, again, so we can think about deviations from the means. And we can already kind of see, okay, so we have one, we have these 2 data points that seem to work in the positive relationship. I can't get my hands in the right places, but positive relationship where they're moving in the same direction, right? These 2 have either both below or both above the mean. I think I'm using the same colors as the last time, but maybe I'm opposite. So that is working in the negative sense, okay? And then this last one here, we don't actually know. So this is right on the mean for one of them. So we'll talk about what that does to our calculation here in a second. So again, what we're doing is kind of weighting the impact of these different data points, and we can probably expect that we'll probably have a positive correlation, but let's figure out exactly what that correlation is. This is going to be a little cumbersome because we have to calculate our numerator, but then we also have to deal with the standard deviations on the bottom. So the first thing I'm going to do is just calculate the deviations from the mean. Okay, and so let's do x minus x bar. Okay, and then so I'm just kind of switch up colors just to make it a little easier to read, but they're not really connected to those circled values down there. So x minus x bar, this is going to be 4 minus 7, right? The x bar is 7, so this will be 6 minus 7, 8 minus 7, and 10 minus 7. Okay, and we can put those as their exact value, but we can do that later as well. Okay, let's calculate y minus y bar. Okay, and here y bar is 4, so we have 1 minus 4. We have 5 minus 4. 4 minus 4, that's that equal to the mean, and then we have 6 minus 4. Is a 4. Okay. And then, so all we have left to do for the numerator is we need to smush these together. Let's multiply these together. So x minus x bar times y minus y bar, okay, is the following. So this is going to be minus 3, minus 1, 1, and 3, right? So I'm just doing these calculations. Now, as I said, it's important that we carry with the negative sign. Okay, so don't drop that. And then we multiply, so this will be times negative 3. This is positive 1, this is 0, and 2. Okay, and so now let's go ahead and just finish that out. That's going to be 9, right? So that becomes a positive impact to our correlation. So just to be clear, that 9 is coming from down here, okay, the lower left. Yes, they're both below the mean, but because they're both going in the same direction, they're both below the mean, that's a positive impact on our correlation because that's a positive relationship, right? So both below the mean and both above the mean, those two quadrants are working to push towards a positive correlation. And so because they're both negative, that cancels out and we get a positive 9. Now this negative 1 is this red circled one up here. Just to add to more complexity, I'll circle it in orange. But that is a negative relationship. Okay, so we have one of them, which is, so we're below the mean in x, but above the mean in y. And so we have a negative times a positive, and that's going to give us that negative impact. Okay, so let's finish out this calculation. We have 0 and then 6 for that top right. So 0, that's the one that falls right on the mean of y. Okay, and so why does it make sense that that's 0? Remember, what we're talking about is how do these move together? Well, if we think about it in terms of deviations from the mean, x increased and y stayed the same. So y didn't even move. So they didn't move together, they didn't move opposite because y stayed constant. And so that adds nothing to our calculation. It doesn't work towards a positive or a negative relationship. What it is going to do is kind of dampen our end result, right? Because this is going to count in our n minus 1. It's going to add to what we divide in the numerator, what we divide in the denominator, but it's not adding either positive or negative to the sum. So the next thing, just like with standard deviation, we're going to add these together. So we get, what is this? 15 minus 1 is 14. Okay, and that's the numerator of our calculation. So let me just write this out in a slightly different color so it pops out a little bit more. So we have r is equal to 14 over n minus 1 sx/sy. Okay, so we're almost there. We just have to calculate 2 standard deviations, which of course is quite simple. No, but we are on our way to calculating that. So we've already done the deviations from the mean, right? So in essence, what do we have left to do for standard deviation? We need to square those deviations. So I'm just going to continue our chart here. I'm going to square these deviations. And then what's left? We divide by n minus 1, take the square root. Okay. Yeah. Give me just 1 second to check something before I lead us astray. I would just want to verify that my notation is matching. Yeah. So yeah. So just want to verify that I made a mistake up here. So we didn't quite have the s. We need to take the standard deviation, right? So that would have been s squared. Because we'll need to finish that out here. So apologies for having you confused looking at the wrong equation for s. Okay, so let's do this. So this is -3 squared, which is 9. We get -1 squared, which is 1. And 1, and then 3 squared is 9. So we get a sum of, I think this is 20. We're going to divide. Let me get out of the way here. We're going to divide by n minus 1 and take the square root. So sx is square root of 20 over 3, which I get as 2.58. You can always double check my math. And then let's do sy. So y minus y bar squared is 9. That's a 9. 1, 0, 4, I believe, which gives us 14. So sy is the square root of 14 over 3, which again I get as 2.116. Okay, so now we have sx and sy. So let's go back and plug that into our correlation. 14 divided by 3 times 2.58 times 2.16. Okay, smush that all together, and we have r is equal to 0.8366. Okay, and that's our correlation. We have a correlation of 0.8366. That is the relationship. How well do these two variables move together? Okay, get out of the way. We have we'd probably say a strong positive correlation. Again, I've made this data up, but that's how we might report it. We might say, 0.84 and 0.8366. A couple things to note. So maybe should have mentioned this along the way, but the moment we get 14 here, we know we have a positive correlation, okay? Because that's not a negative number. So the only place a negative can show up in our correlation is when we add these together. Okay, why do we know that? Well, let's think about the bottom of the equation. n minus 1 can't be negative, right? We're not going to have an observations of 0 to be -1. Okay, so it can't be negative. That's a positive number. And what do we know about standard deviations? They have to be positive. So sx and sy are positive numbers. So just as you're doing your calculations, just know that when you sum up and you get positive number, you're going to have a positive correlation. If you get a negative, you're going to get a negative correlation. So just ways you can kind of double check as you're going along. It shouldn't switch. So once you plug in a positive number here, you shouldn't have a negative come out. Uh, yeah. So that's a rough, or that's our first calculation of a correlation. Okay. Again, a lot of times we'll just have Excel or some package do this for us, but it is important that you can conceptualize and know what's happening in the back when you're plugging these things in. Okay. And also because you should be able to expect, even looking at a scatter plot here, oftentimes we can kind of expect, okay, this looks like it's going to be positive, especially when you do kind of the quadrant kind of, whether it's visually or you could draw these as well, right? We could draw in some quadrants and say, okay, seems like we have some positive relationship happening. And so it's good to always be able to expect what the value is going to spit out. A couple other things to just draw your attention to is that we have calculated R, the correlation coefficient. Now, when you get into the assignment and what we'll talk about probably Friday when we're in Excel, sometimes you're going to have to calculate what's called R squared. Okay, and this is, loosely speaking, a measure of how well can we predict one variable using the other. And R squared is just what you would expect. It is R squared. It's R times R. So in our case, I think this becomes right at about 0.7. So 0.83 times 0.83, it's like 0.9 or 0.69989 or something. So R squared is 0.8366 times 0.8366. Okay, so we're not tricking you there. The calculation is as simple as it seems. So just while we've calculated a correlation, we might as well calculate the R squared here, just so you see it one more time. So hopefully you're not caught off guard when you do that. Now, again, correlation by itself, useful. We can talk about the relationship between two variables using this. We can say this is a strong positive correlation. We can say, hey, I calculate, or I ran the numbers on these two variables and they have a correlation of positive 0.3 or 0.8366, and that tells us something. That tells, you're working in an office and you have some other statistical, other people that have taken the stats or do data analysis. You can rattle off a correlation, and those people are going to be able to build a mental picture, right? They might get a feel for what that scatter plot looks like. Much like we said with standard deviation, the moment you tell somebody I have a normal distribution with, a standard deviation of 4, they're starting to build that mental picture. Correlation is a similar sense. We can start getting a sense from those simple statistics, summary statistics of what this data looks like. And then again, as we'll turn and look at on Friday, this is the linchpin of which regression is built. And on Friday, we'll look at regression, and again, to foreshadow where we're going, regression is, loosely speaking, that best fit line. Okay, so is that the best fit, or is this the best fit? How do we pick out which is the best line to summarize our data and summarize the relationship between the data points? So we'll stop here, but that's kind of the introduction to correlation, and we're ready to jump into regression soon. So just a reminder, I have office hours later today and on Friday, and I don't know if I mentioned it, but I'll have them in the next couple weeks too as we go into studying for the final. So I'll stick on here for a couple minutes as well if people have questions now. Otherwise, in about an hour, I'll be back in the same Zoom room.